Hello, my name is Greg Rose, and what I'd like to do today is to briefly tell you about some studies we've been performing to examine the effect of cognitive training on brain plasticity. The goal of this particular study was pretty straightforward, and that's simply to determine whether cognitive training affects resting state brain connectivity, and we used functional magnetic resonance imaging to examine this question. So what are resting state networks and what is resting state network connectivity? Well, we all have this idea that brain regions have to work together to get anything done. Originally, this was thought to happen only when a subject was engaged in a specific activity. But about 25 years ago, it was found that, in fact, even under task-free conditions, when the brain is supposedly at rest, that distinct brain regions coordinate with each other. And this was demonstrated, again, using functional magnetic resonance imaging. Here in the image on the left, or the figure on the left, you can see that there is a very slow cycling of the bold signal coming from the scanner. And further, if you compare the signal coming from the yellow region and the orange region, you can see that they actually coordinate their activity remarkably well. So by examining a number of different brain regions and looking at those that are actually cycling together, one can define a particular network. In this case, as can be seen below, the sensory motor network. And the interesting thing about this is that the strength of these connections in the resting state actually predicts how well a subject will actually do in the types of tasks that would normally engage that network. So a number of different networks have been described. You can see from this figure that actually several of them have to do with, just sort of sensory motor function, the visual, sensory motor, auditory networks. We were more concerned or interested in those that were involved with cognitive function. And so the four networks we chose to focus on were the default mode network, the dorsal attention network, the salience network, and the frontoparietal control network. And you can see how these networks are organized by looking at the schematics for each that's showing a sagittal, a coronal, and an axial section with the nodes of the network defined by the colored dots. So very briefly, what do these networks actually do? What's their involvement in behavior? Well, the default mode network is basically engaged in mentation and internal processing, the I'm thinking network. The dorsal attention, the initial interaction with the world, what's going on. The salience network, what's important, all these experiences I'm having. And the frontoparietal control network in formulating responses to specific situations. In our study, we were interested in the strength of connections both within a particular network as well as the potential connections between the networks. So the task we chose to examine was part of the Arrowsmith Summer Cognitive Intensive Program. It's called the Symbol Relations Task, and it's a seemingly simple task that involves reading an analog clock face and simply entering the time that's demonstrated by the hands. In this picture, you can see that the clock only has one hand, and so the subject would simply type in on the keyboard 8. As the subjects get better at a particular level, then additional hands are added to the clock. So hours, then minutes, then seconds, then things one wouldn't normally see on a clock face. Days, weeks, months, etc. So that the task can actually get incredibly complicated. The training in this cognitive intensive program is itself very intensive, up to 5 hours a day in 30 to 40-minute blocks with breaks in between for 6 weeks. So how did our subject pool do in this task with the training? We had a total of 22 subjects who participated in the training and from whom we also got good imaging data. You can see here on the left that at the beginning, prior to training, that the individuals as a group did relatively poorly. and that, as expected, they improved significantly by the end of training. What was important and useful for us experimentally was that the variability that was seen between subjects, both at the start and at the finish, and in the degree of improvement. So the reason that there aren't 22 circles in this figure here on the right is because several of the subjects had exactly the same start and finish levels. So if we look at what happened as a function of the symbol relations training with respect to the network connectivity in the networks we were examining, we found here on the left, as shown here on the left in an axial section, that if we subtracted the signal, the connectivity at the beginning of training from that at the end of training, that there were 4 connections that showed significant strengthening. And you can see that they are strengthened by the fact that the colors range from sort of yellow to red. The F values are shown in the scale bar up here. All of the connections had in common a particular node, the right lateral parietal node of the default mode network. And the connections were mostly to different nodes in the salience network and one in the frontoparietal control network. To further take a look at the relationship between the behavioral change in behavioral performance and the change in network connectivity, we actually isolated or chose just a subpopulation of subjects to examine. And these were all those that began with a score of 2, which led us to think that there would be the opportunity for maximal improvement during training. And you can see that it turned out that there were 5 subjects in each group, that the group that were the least improved, the red bar over here, hardly showed any gain in performance at all, while those in the most improved group really showed an impressive gain as a function of training. So if we did a similar analysis to the overall group, looking at the change in the strength of the resting state functional connectivity, we can see that, in fact, in the least improved group, there were no significant changes at all, whereas in the most improved group, again, there were a host of changes, mostly strengthening of connectivity and connections all between this particular node in of the default mode network and nodes within the salience and frontoparietal control networks. In addition, however, in this subgroup, there was a significant weakening of a connection between the default mode network and a node in the dorsal attention network. So we, as I mentioned earlier, we wanted to examine the overall connectivity both between and within networks. So we first looked at within network connectivity values, and we found that those did not change at all after symbol relations training. And a reason for this could be that the R values for the nodes within a given network were actually fairly strong to begin with, averaging about 0.5. In contrast, the between network connectivity values were much lower, ranging from essentially nothing to a weak 0.22. However, we did find, as anticipated from looking at our individual results, that the overall between network connectivity between the default mode network and the salience network or the frontoparietal control network did change as a function of training. And so you can see in these 2 figures down here that if one takes a look at individual performance in symbol relations, the improvement, and looks at the change in between network connectivity, that in both cases, the slope of the line is positive and indicating that there's actually a relationship between the degree of improvement and the change in network, the strengthening of network connectivity. Those actually that didn't do as well actually had relatively weakened connectivity. So in summary, and to provide a few preliminary conclusions, we can definitely say that training in the Arrowsmith Cognitive Intensive Program strengthened resting state network connectivity. We also know that the change was proportional to the improvement over the training interval, and that the connections between the salience and default mode networks were particularly effective. So putting these things together, we are coming to the preliminary conclusion that enhanced resting state connectivity could be responsible for the improvement in task performance. A key question, however, is how these changes in brain plasticity affect performance in tasks other than symbol relations. And as you can see, as detailed here in red, we've done pilot work looking at the effect of symbol relations training on various cognitive tests in the Woodcock-Johnson 4 battery, and have seen significant improvement in a variety of these tests. And my colleague, Dr. Mohammed Yagane, is actually presenting those data at this meeting. So if you have the opportunity and interest, you can go and listen to her talk. In terms of our next steps, what we want to do, of course, is to increase our sample size. This hasn't been possible during the COVID time, but hopefully soon again we'll be able to image. We want to examine an untrained control group. There's a lot of literature suggesting that resting state connectivity is stable within an individual, but we would like to confirm that there just wasn't a change over time in our sample that could have led to any of the network changes that we observed. And perhaps most importantly, we want to repeat the imaging and neuropsychological assessments over time. The idea of plasticity, changes in brain plasticity, is that it predicts that there should be long-lasting improvements in behavioral performance. Whether these are associated with lasting changes in resting state connectivity, we don't know, just as we don't know yet whether or not these performance changes last and extend to other domains. So that's all I have to say today. If you can ask questions, that would be great. If you can't, my email address is on the first slide, and I'd be happy to receive a note from you and respond.